Have you ever just looked up at a huge airplane? I mean, a massive jet lifting off the ground and thought, how does that really work? Well, the secret isn't just about air moving over a wing. It's hidden in the invisible, swirling world of air, all governed by a set of rules that are, honestly, surprisingly elegant. Today, we're going to pull back the curtain on the 150-year-old laws that actually make modern flight possible.
All right, so here's the game plan. First, we're going to step into the theoretical world where these rules were first figured out. Then, we'll unpack the laws themselves, one by one. After that, we'll connect the dots to see how they create real-world lift. And finally, we'll uncover the one crucial missing piece that links this perfect theory to our, messy reality.
So yeah, let's just start with that big central question. It's a mystery that's had scientists scratching their heads for centuries. And spoiler alert, it's not just that old story about air moving faster over the top of the wing. The real secret to flight is way more interesting, and to really get it, we've got to simplify things a little bit first. Look, the way air moves is incredibly complicated. It's chaotic. So to even begin to make sense of it, the early pioneers of fluid dynamics had to create a simplified model. Think of it like a theoretical playground where they could figure out the basic rules without all the messiness of the real world getting in the way. And welcome to that playground. It's the world of the ideal fluid. Now, this stuff doesn't actually exist, okay? It's a totally imaginary substance that you can't squish, and it has zero stickiness or friction, what scientists call viscosity. But by studying how this perfect fluid would behave, they could finally isolate the absolute core principles of how fluids move. So, it was right here, in this perfect world of ideal fluids, that a 19th century German scientist named Hermann von Helmholtz laid down the absolute bedrock laws for those swirls we see in fluids, what we call vortices. Before we get to the laws themselves, we've got to get one key concept down: vorticity. Just think of it as a measure of the local spin in the fluid, like a tiny spinning packet of air. Helmholtz's laws are basically the rule book for how these spinning little packets have to behave. Okay, here they are, the big three. Law number 1 says a vortex's strength is the same all the way along it. Makes sense. Law 3 says basically, once a bit of fluid starts spinning, it just keeps on spinning with the same strength as it moves. But the one that changes everything for us, the absolute key that unlocks flight, is law number 2. A vortex can't just appear out of nowhere, and it can't just stop in the middle of the air. It has to form a complete closed loop. So we've got this abstract rule for a perfect imaginary fluid. A swirl has to be a closed loop. Great, but how on earth does that explain how a 300-ton airplane stays up in the sky? Well, this is where the theory does something truly brilliant and connects to reality.
Let's think about this for a second. We know the wing is generating lift, and that lift is a kind of vortex. But a wing has tips, right? It has a start and an end. So if Helmholtz's second law is true, and the vortex can't just stop at the wingtip, what gives? What happens? The secret lies in something called circulation. This is basically a rotating flow of air that gets bound to the wing. It travels right along with it. In other words, the wing literally carries its own vortex with it as it flies. And here it is. This is the aha moment. If the wing has this bound vortex creating lift, and that vortex physically can't go past the wingtip, well, it can't just vanish into thin air. To obey Helmholtz's law, it has to do the only thing it can do. It has to turn. And this gives us the whole beautiful picture. That bound vortex running across the wing turns down at the wingtips and streams behind the plane as two trailing vortices. The whole system then connects all the way back to a starting vortex that was shed way back when the plane first started moving. It all forms one giant closed loop. It's famously known as the horseshoe vortex. So why does this old 19th century idea still matter so much? Because understanding this vortex system is absolutely crucial for designing efficient aircraft. It lets engineers predict and, more importantly, minimize something called induced drag. That's energy just wasted by those trailing vortices. For a big airliner, that means burning less fuel. And for a modern drone, a UAV, getting this right is the difference between staying aloft for a few hours or for several days. This old law is still at the very heart of cutting-edge design. But here comes the twist. As beautiful as this model is, remember, it was dreamed up for a perfect frictionless world. And our world is, well, it's not that. And this leads to a pretty major paradox. So here's the problem. The ideal fluid theory is fantastic at predicting lift. It gets that part right. But because it assumes there's no friction, it also predicts there should be zero drag. That's the famous Dahl-Lambert's paradox. And we all know planes experience a lot of drag. So what's missing? What's the missing piece of the puzzle? It's that real-world stickiness of air we talked about, viscosity. The person who finally cracked this puzzle was another German physicist, Ludwig Prandtl. In 1904, he came up with a truly groundbreaking idea that finally built a bridge between the perfect world of ideal fluids and the practical world of actual engineering. So let's take a look at what this next giant leap in understanding flight really was. Prandtl's big idea is known as boundary layer theory. He basically said, hey, what if all those messy, complicated effects from friction are actually stuck in a really, really thin layer of air right next to the wing's surface? Outside of that tiny boundary layer, the air behaves almost perfectly, just like Helmholtz imagined. It was a genius move that connected both worlds. And that one idea, that thin, sticky layer, explains the true origin of drag and a ton of other complex aerodynamic effects. It lets us use the elegant math of the ideal world while still accounting for the friction of the real one. But how exactly does this one thin layer of air completely rewrite the rules of flight? Well, that's a fantastic question, and we'll dive deep into it in our next explainer.